If you were to board a commercial airplane and fly toward our nearest stellar neighbor, your journey would last roughly 5 million years. 200,000 generations of your descendants would live and die before ever reaching the destination. Yet, in the grand map of the Milky Way, the 25 trillion mile gap is smaller than a single grain of sand in a football stadium. For 60 years, we looked at the bright point of light in the constellation Centaurus and called it hope. We imagined oceans shimmering under alien suns and wondered if life was gazing back at us across the void. But what if the very stars we called our first stepping stones are actually cosmic death traps? Are we prepared to accept that the place we thought was a sanctuary for life is actually a nightmare of radiation 10,000 times more violent than anything our Earth has ever experienced? When the James Webb Space Telescope turned its massive golden mirrors toward Alpha Centauri, it didn't find the second Earth we were promised. Instead, it revealed a story of extreme violence. The data streaming back to Earth tells us that these promising worlds are almost certainly dead. They are sterile, stripped of their atmospheres, and bombarded by relentless energy for decades. Alpha Centauri was the center of our interstellar dreams, fueling projects like Breakthrough Starshot that aimed to send tiny probes to these stars at 20% the speed of light. We believed we could reach another star within a single human lifespan. But the reality James Webb has uncovered is far more disturbing than we ever imagined. The excitement reached a fever pitch in 2016 when astronomers confirmed the existence of Proxima b, a planet orbiting the smallest and closest member of the Alpha Centauri system. This star, Proxima Centauri, is a red dwarf only about 1/7 the diameter of our Sun. Despite being our literal next-door neighbor in the cosmos, this tiny stellar furnace glows so dimly that it remains completely invisible to the naked eye. You would need a telescope just to see the closest star to our solar system. Proxima b seemed like the perfect candidate for a second home. It possesses roughly 1.3 times the mass of Earth and sits comfortably within the habitable zone, the Goldilocks region, where temperatures could allow liquid water to pool on the surface. Because its parent star is so cool and dim, the planet must huddle incredibly close to receive enough warmth. Orbiting at a distance of just 7.5 million kilometers, that is 20 times closer than Earth orbits the Sun. For years, we dared to dream. Scientists speculated about alien oceans shimmering under a red sun and clouds drifting through a foreign sky. It felt as though the universe had intentionally placed a habitable world exactly where we needed it, close enough to study, and eventually, close enough to visit. But our perspective shifted forever in December 2021 with the launch of the James Webb Space Telescope as the most powerful observatory ever constructed. Its golden mirrors were designed to peel back the layers of cosmic mystery with unprecedented clarity. When James Webb finally set its sights on Proxima b, it didn't find a peaceful sanctuary. Instead, it captured a reality of terrifying stellar violence that shattered decades of hopeful speculation. What the James Webb Telescope found instead shattered decades of hopeful speculation. The observations revealed that Proxima Centauri unleashes stellar violence on a scale far exceeding any previous estimates. This dim red star experiences massive flare events that temporarily increase its brightness by factors of 100 or more. During these extreme outbursts, the star emits ultraviolet radiation at levels that would strip away atmospheric molecules from any planet orbiting in the habitable zone. These flares do not occur occasionally. They are routine, happening multiple times per week, with smaller eruptions occurring every single day. For a planet like Proxima b, there is no escape from this explosive fury. When a major flare erupts, the radiation reaching the planet exceeds the normal stellar output by factors of 10,000 or more. The day side would experience radiation levels that would sterilize exposed surfaces within minutes. Any organism caught without shielding would have its cellular chemistry destroyed almost instantaneously. This is not the gentle warming of a distant sun, but a continuous bombardment of high-energy particles and ionizing radiation that would make the surface of Venus seem hospitable by comparison. Even organisms on Earth adapted to extreme radiation would struggle to survive the conditions that Proxima b endures routinely. James Webb's spectroscopic analysis provided even more disturbing evidence. The spectral data suggested that Proxima b either never developed a substantial atmosphere or lost whatever it once possessed to this relentless radiation. The planet likely presents a barren, rocky surface directly exposed to the vacuum of space, baked by ultraviolet light and bombarded by stellar winds traveling at hundreds of kilometers per second. The absence of an atmosphere on Proxima b carries profound and tragic implications for its habitability. Without a gaseous envelope to distribute heat, the planet cannot move warmth from its blazing day side to its frozen night side. This means that regardless of the temperature, liquid water, the fundamental requirement for life as we know it, simply cannot exist on the surface. Instead, the planet exists as bare rock, exposed to the full, unfiltered fury of its parent star. For decades, Proxima b symbolized our greatest cosmic hope, but the James Webb Telescope has revealed that this stepping stone is actually a death trap. To understand why our nearest neighbor is so violent, we must examine the fundamental nature of red dwarf stars. Our sun generates energy in its core and transports it outward through stable layers, in a process that takes hundreds of thousands of years. Red dwarfs, however, operate much more chaotically. Because of their small mass, their interiors remain fully convective, with hot material rising directly from the core to the surface like water boiling in a pot. This constant churning generates powerful magnetic fields that become tangled and stressed. When these magnetic lines finally snap and reconnect, they release enormous amounts of energy as stellar flares. The scale of this violence is difficult to comprehend. While a major solar flare might increase our sun's brightness by only a tiny fraction, a flare from Proxima Centauri can increase its brightness by factors of hundreds or even thousands. These outbursts release energy equivalent to millions of nuclear weapons detonating simultaneously, bathing any nearby worlds in a lethal glow. To truly understand the nightmare unfolding at Proxima Centauri, we must look at the clock that governs the life of a star. Our sun is a yellow dwarf, a stable and relatively predictable furnace that has provided the steady warmth necessary for life to flourish on Earth. It will exhaust its hydrogen fuel in roughly 5 billion years, eventually expanding into a red giant before fading into a white dwarf. This 5 billion year window is the time frame in which all of human history and biological evolution has occurred. However, Proxima Centauri operates on a completely different scale of time. This red dwarf burns its fuel so slowly that it will continue to shine for trillions of years. This is hundreds of times longer than the entire lifespan of our sun. At first glance, this extreme longevity might seem like a profound benefit for the possibility of life. We often think that more time equals more chances for biological evolution to work its miracles. But the James Webb observations have revealed a much darker reality. Instead of providing a stable cradle for life, this extended lifespan means that any planet orbiting a red dwarf faces a continuous bombardment for billions of years, longer than planets orbiting sun-like stars. While our sun is expected to settle into a quieter phase as it ages, Proxima Centauri shows no signs of slowing down. Despite being roughly 4.8 billion years old, a similar age to our sun, this red dwarf continues to produce violent outbursts at rates characteristic of much younger, more unstable stars. The magnetic dynamo driving these flares appears to operate with sustained intensity throughout the entire lifetime of the star. This means that planets in the habitable zone are not facing a temporary period of youthful violence. They are under an eternal siege. The implications of this reach far beyond the loss of an atmosphere. They strike at the very heart of the chemistry required for life. Life, as we understand it, requires complex organic molecules to form and remain stable over geological timescales. We are talking about the delicate building blocks like amino acids, nucleotides, and lipids that make up cellular structures and drive biochemical processes. Ultraviolet radiation is exceptionally efficient at destroying these molecules. It breaks the chemical bonds and induces harmful reactions that tear these structures apart. Complex organic chemistry simply cannot proceed when its fundamental building blocks are being demolished by incoming radiation as quickly as they form. On Earth, we are shielded from this destruction by a complex system of defenses. Our atmosphere filters out the most damaging wavelengths of ultraviolet light before they ever reach the ground. Specifically, the ozone layer in our stratosphere absorbs the radiation that would otherwise sterilize every environment on the surface. Early Earth may have lacked this ozone shield, but life found a sanctuary in the depths of the oceans. Hundreds of meters of seawater provide a barrier against ultraviolet radiation that is just as effective as our modern atmosphere. It was only after photosynthetic organisms produced enough oxygen to form the ozone layer that life could finally leave the water and colonize the land. But the James Webb data confirms that Proxima b cannot replicate this protective pathway. Without an atmosphere to absorb that radiation, the surface of the planet receives the full force of the star's violent output. Because there is no surface water to provide a refuge for early organisms, there is no protected environment where life could even begin to evolve. And because the planet lacks the geological activity necessary to produce volcanic gases and maintain atmospheric pressure, there is no way to replace what has been lost. Every single pathway that allowed life to emerge and survive on Earth is effectively blocked on Proxima b. The fundamental problem is not a flaw in the planet itself, but the star it orbits. No planetary feature, no matter how robust, can compensate for a stellar environment that continuously destroys the basic requirements for habitability. If the planet had a thick atmosphere, it would be stripped away by stellar winds and flare radiation. If it had a strong magnetic field, it would be overwhelmed by a particle bombardment that exceeds anything we experience in our solar system. If it had an ocean, the water would be vaporized and broken down by ultraviolet light. The violence inherent in the nature of Proxima Centauri dooms any world that orbits close enough to feel its warmth. This is the measured certainty that James Webb has brought to the table. For years, scientists had theoretical warnings about flare activity and atmospheric stripping around red dwarfs. But suspicions are not data, and warnings are not measurements. The telescope has provided quantitative proof of flare frequencies and radiation intensities that paint an unambiguous and heartbreaking picture. Our nearest potentially habitable neighbor is almost certainly a dead world. The hope that sustained generations of dreamers has finally evaporated under the harsh light of observational reality. When we calculate the actual radiation doses, the numbers are terrifying. Organisms on Earth's surface receive natural background radiation measured in millisieverts per year. On the surface of Proxima b, even during calm periods, the radiation doses would be measured in sieverts, roughly 1,000 times higher than Earth's annual background every single hour. During the frequent flare events, those doses would spike to hundreds of sieverts within minutes. These are levels that would instantly destroy any biological material known to science. Under this continuous bombardment, the chemical foundations of life simply cannot accumulate. Even burial under the ground offers little comfort. Cosmic rays can penetrate rock to depths of several meters. Only burial under tens of meters of solid rock would provide adequate shielding. But such deep, isolated environments lack the energy sources and chemical flows that life needs to exist. Proxima b is not just an airless rock. It is a world where the very possibility of complexity has been stripped away. While the violence of Proxima Centauri is enough to extinguish our dreams of a nearby sanctuary, it represents only one member of the Alpha Centauri system. For generations, astronomers and dreamers held on to a secondary hope, the primary binary pair, Alpha Centauri A and B. These are not the small, angry red dwarfs that dominate the galaxy. Instead, they are sun-like stars, majestic, stable, and seemingly capable of hosting worlds just like our own. Surely, somewhere within this triple star system, a place exists where life could take root. However, the latest data from the James Webb Space Telescope reveals that even these promising candidates face challenges that make habitability virtually impossible. The problem shifts from individual stellar violence to the fundamental, chaotic dynamics of how a triple star system forms and matures. What James Webb discovered about Alpha Centauri A and B completes a tragic picture of a stellar neighborhood that looks hospitable from a distance but proves deadly upon closer examination. Alpha Centauri A is a stunning mirror of our own sun. It shines with a warm yellow light, possessing about 10% more mass and a 23% greater diameter than our star. Its surface temperature reaches approximately 5,800 Kelvin, producing that familiar golden glow we recognize from our own G-type star. Analysis reveals a chemical composition nearly identical to the Sun, suggesting both stars were born from similar interstellar material in their respective stellar nurseries. If you stood on a planet orbiting this star, the sky might look hauntingly familiar. Its companion, Alpha Centauri B offers a different but equally beautiful sight, glowing with the cooler orange hue of a K-type star. The stellar furnace contains roughly 90% of our Sun's mass and produces about half the luminosity. With surface temperatures hovering around 5,300 Kelvin, it is noticeably cooler than the Sun, but it still possesses more than enough energy to warm a planet within a meaningful habitable zone. From Earth, these two stars are so close that they appear as a single gleaming point of light. Only a telescope can reveal their binary nature. These two suns engage in an elaborate gravitational dance, orbiting each other at distances that range from 11 to 36 astronomical units. To put that in perspective, this is a span comparable to the distance between Saturn and Pluto in our own solar system. Their orbital period lasts approximately 79 years, meaning they complete less than one full orbit during a human lifetime. A person born when the stars were at their closest separation would be reaching middle age by the time they drifted to their maximum distance. Unlike the volatile Proxima Centauri, these larger stars have a stable, layered internal structure that produces relatively calm surfaces. They experience activity cycles similar to our Sun's 11-year sunspot pattern, with only modest variations in energy output. This optimistic assessment, however, collapses when viewed through the lens of gravitational dynamics. Alpha Centauri A and B do not simply coexist in peace. Their elliptical orbit brings them close enough every 80 years to gravitationally perturb everything in their vicinity. This periodic disruption creates conditions that are fundamentally hostile to the stable planetary orbits that life requires. In the world of orbital mechanics, two massive bodies orbiting each other create a complex and shifting gravitational field. Any third body, like a small planet trying to find a home around one of these stars, must contend with constant gravitational tugs from the other star. Over time, these perturbations accumulate, gradually shifting a planet's path until a stable, circular orbit becomes a wildly eccentric and unstable ellipse. James Webb set out to find these hidden worlds using its incredible infrared sensitivity. The telescope was designed to detect the faint thermal signatures of Earth-sized planets by looking for the mid-infrared light they radiate. To see these tiny, glowing dots against the overwhelming glare of the twin suns, James Webb uses sophisticated coronagraphs, tiny masks that block the central starlight while allowing the light from the surrounding regions to reach the detectors. The observation campaign spanned 18 months, a temporal baseline that allowed astronomers to track any potential orbital motion. A real planet would shift position predictably according to the laws of motion, while background objects would remain stationary. The data did not reveal a hidden family of planets. Instead, it showed clear evidence of disrupted circumstellar material around both stars. When stars are born, they're surrounded by rotating disks of gas and dust from which planets eventually coalesce. These protoplanetary disks contain the raw ingredients for life: silicate dust for rocky cores, ice particles for water, and gas for atmospheres. The orderly architecture of our solar system is a result of these processes, occurring in a calm environment 4 billion years ago. But at Alpha Centauri, the spectral signatures tell a story of catastrophe. The gravitational interaction between the two stars during their closest approaches stirred and scattered the disk material rather than allowing it to settle into stable worlds. Computer simulations confirm that tight binary pairs like these regularly truncate or destroy the planet-forming disks around them. Particles that should have followed circular paths were suddenly pulled by the companion star, their orbits becoming eccentric and causing them to collide at high velocities. These were not constructive collisions that build planets. They were destructive impacts that ground material into smaller and smaller fragments. This destruction unfolded over millions of years. Initially, the perturbations merely elongated the paths of dust grains and pebbles. But as the eccentricities grew, particles began crossing paths at tens of meters per second. At these speeds, silicate grains shatter rather than stick together. The aggregates that had just begun to form were pulverized back into their constituent particles. The constructive phase of planet building was reversed into a cycle of destructive grinding. As the violence escalated, impacts reached hundreds of meters per second, vaporizing solid material into clouds of gas and microscopic debris. The energy released in these hypervelocity collisions drove off the volatile compounds, the very water and gases needed for oceans and atmospheres. The nursery of worlds was transformed into a demolition zone. The 11 to 36 astronomical unit separation between these stars falls into a dead zone for planet formation. It is a configuration that maximizes interference with the very regions where temperatures would permit liquid water to exist. The same proximity that makes Alpha Centauri A and B so bright and prominent in our sky is exactly what doomed their potential to host life. The James Webb Space Telescope does not just see stars and planets. It sees the thermal echoes of history written in infrared light. When it turned its gaze toward the primary stars of Alpha Centauri, it was searching for the building blocks of worlds, the remnants of the massive clouds of gas and dust that should have birthed a family of planets. What it found instead was a sparse and haunting debris disk, a collection of cosmic wreckage that tells a story of failure rather than creation. Unlike the rich, vibrant planet-forming disks that surrounded our young sun 4.5 billion years ago, the material around Alpha Centauri is scattered and thin. The total mass of this detectable debris amounts to less than 1% of the material that built the rocky, terrestrial planets in our own solar system. This infrared signature acts as a celestial autopsy. By analyzing the different wavelengths of light, James Webb was able to map the spatial distribution of this material with unprecedented detail. Cold dust farther out emits at longer wavelengths, while warmer material, closer to the star, glows differently. This map revealed a chilling architecture. The inner edge of the debris disk around Alpha Centauri A lies much farther from the star than the habitable zone. Every scrap of material that once occupied the region where liquid water temperatures might prevail has been cleared away entirely. Inside this boundary, the telescope detects essentially nothing but empty space and the star itself. This inner clearing is a testament to billions of years of gravitational processing and destruction. The raw materials required to build a world were not just used up, they were systematically removed. Any material that once filled the inner system was either ground into dust so fine that it was blown away by stellar radiation pressure, or it was pushed onto chaotic trajectories that caused it to fall into the star or be ejected into the cold void of interstellar space. The habitable zone, the very place we hope to find life, has been swept clean, even if the laws of gravity somehow allowed for stable orbits in this region today. There is no longer anything left from which to build a world. The spectroscopic analysis of this wreckage provides even more devastating evidence. The material consists primarily of silicate dust, similar to the asteroids found in our solar system, but the particle sizes indicate a history of collisional grinding rather than accretional growth. In a successful solar system, small particles stick together to build larger bodies in a process called accretion. But in Alpha Centauri, the gravitational perturbations of the twin suns increase collision velocities beyond the threshold for constructive accumulation. Bodies that tried to form were simply smashed apart. This chemical evidence suggests that any solid material remaining in the system was baked dry long ago. There is no evidence for the volatile, rich compositions that would indicate water-bearing worlds or the presence of substantial ice content necessary to deliver oceans to forming planets. The repeated gravitational stirring prevented material from ever settling into the cold regions where water ice could persist. Instead, the entire circumstellar environment experienced massive heating events that drove off volatile compounds. Whatever worlds might have attempted to form from this material would have been dry from their very birth, lacking the water necessary for surface oceans or even a hint of atmospheric humidity. A planet that forms without water cannot magically acquire oceans later. The delivery systems of water, bearing asteroids and comets that bless the early Earth, are completely absent here. The tragedy of Alpha Centauri was then likely sealed by a final cosmic intruder, the arrival of Proxima Centauri. Current theoretical models and James Webb's data suggest that this red dwarf was not born alongside the primary binary stars, but was captured much later in the system's evolution. The capture of a passing star is a violent gravitational event. As Proxima Centauri drifted into the gravitational sphere of the Alpha Centauri binary, its initial trajectory would have carried it back out into space. But at its closest approach, just enough kinetic energy was extracted to bend its path into a permanent bound orbit. The laws of physics demand that this excess energy be absorbed by other bodies in the system. Any planets or planetesimals that had managed to survive the earlier binary disruptions would have served as the energy repositories for this capture. They would have absorbed Proxima's excess kinetic energy through gravitational interactions that simultaneously destabilized their own fragile orbits. This capture event, essentially pressure, tested whatever planetary systems remained, and the test proved too severe for any world to survive. The gravitational perturbation from this passing red dwarf would have scattered any remaining planets, pushing them onto chaotic trajectories that led to their ultimate ejection from the system, or a fiery collision with their parent stars. The arrival of our nearest neighbor was the final blow to any hope for a habitable Alpha Centauri. The violence that characterized the formative epochs of this system has left permanent scars that no amount of time can heal. The raw materials for building a home were destroyed, the chemical inventory for oceans was driven away, and the orbital stability required for life was shattered. James Webb has shown us a system that is cleaning up its own wreckage, sweeping away the final evidence of what might have been. The James Webb observations have done more than just identify the absence of planets. They have provided a direct look at the physics of why they failed to form in the first place. To understand the tragedy of Alpha Centauri, we must look at the way worlds are built. In a successful system like our own, the process of planet formation is an orderly, constructive growth called accretion. It begins with microscopic grains of dust that gently collide and stick together, eventually forming pebbles, then boulders, and finally the massive planetesimals that become the cores of worlds. For this to work, the collisions must be slow and gentle. In our own solar system's infancy, particles moved at an average speed of roughly 1 meter per second or less, a pace slow enough for dust to adhere upon contact. But the gravitational stirring in the Alpha Centauri system changed those rules entirely. The proximity of the twin suns elevated collision velocities to tens or even hundreds of meters per second. At these speeds, the constructive phase of building worlds reverses into a cycle of destructive grinding. Instead of sticking together, silicate grains shatter into pieces. Any aggregates that manage to form briefly are pulverized back into their constituent particles by the next impact. The James Webb Telescope specifically searched for evidence of ongoing accretion or coalescing planetesimals, but it found only spectral signatures consistent with grinding and destruction. The remnants of this system are not a nursery. They are the debris of a billion-year-long demolition derby. This velocity enhancement is the result of a phenomenon known as eccentricity pumping. As material orbiting one star feels the periodic gravitational tugs of the other star, its path becomes increasingly elongated. This creates a massive variation in speed. Objects at the same distance from their star find themselves moving at wildly different velocities when their paths cross. This isn't a temporary glitch. It is an inexorable consequence of celestial mechanics. While two-body motion, one star and one planet, is stable and predictable, the introduction of a second star creates a three-body problem. The resulting trajectories are chaotic, resisting simple prediction, and ensuring that the orbital parameters of any surviving material are constantly being shifted and spread. Even after billions of years of evolution, the gravitational environment remains too disturbed for constructive accumulation to ever begin. Perhaps the most haunting realization provided by this data is the time problem. Life on Earth required an immense amount of time to develop. It took several 100 million years for prebiotic chemistry to spark into the first living cells, and another 3 billion years to produce complex multicellular organisms. Intelligent life, like us, only appeared in the final few million years of that 4 billion year journey. For life to have a chance, a planet must maintain stable conditions over these vast geological timescales. The orbital stability calculations for hypothetical planets around Alpha Centauri A and B show a catastrophic mismatch. Even orbits that appear marginally stable only persist for millions of years before the accumulated gravitational perturbations lead to a collision or ejection from the system. This time frame is 3 orders of magnitude shorter than the time life required to emerge on Earth. Even if a habitable planet had somehow defied the odds and formed in this system, it would have been destroyed long before the first spark of biology could ignite. The gravitational clock in this system simply runs too fast for biology to keep up. This discovery has profound implications that ripple far beyond our nearest neighbors. Roughly half of all sun-like stars in the Milky Way exist in binary or multiple star configurations. If the Alpha Centauri case is representative of these systems, then half of all potential planetary hosts in our galaxy may be fundamentally unsuitable for life. The galaxy contains far fewer promising targets for the search for life than our most optimistic estimates once suggested. James Webb's broader survey of other binary systems reinforces this grim conclusion. The telescope has examined dozens of binary pairs with separations similar to Alpha Centauri A and B, between 10 and 50 astronomical units. Across the board, these systems show a dead zone for planet formation, where circumstellar material is either truncated or completely absent in the habitable regions. While confirmed planets do exist in some binary systems, they occupy very different architectures. They are either found in extremely tight binaries, where the two stars function as a single gravitational object, or in extremely wide binaries, where the stars are too far apart to interfere with each other. The intermediate range that Alpha Centauri occupies appears to be a genuine wasteland. For decades, we had theoretical frameworks and mathematical models that predicted these constraints, but without direct measurements, there was always room for a sliver of hope, a belief that nature might find a way around the math. James Webb has now closed that loophole. Alpha Centauri is not a strange anomaly. It is a representative example of a common, lethal phenomenon in our galaxy. We now know that even if a planet survived the chaos of formation, it would still find itself in a radiation prison. Imagine standing on a world where the sky never darkens and the ground never cools. One face of the planet roasts under eternal daylight, while the opposite hemisphere freezes in perpetual night. The boundary between these extremes, a narrow twilight zone circling the globe, experiences constant atmospheric turbulence as massive temperature differentials drive hurricane-force winds. Storms rage perpetually along this line, carrying heat from the blazing dayside toward the frozen nightside in a desperate atmospheric attempt to equalize temperatures that can never truly balance. This is the grim fate of tidally locked worlds. These are planets that orbit so close to their stars that gravitational forces have synchronized their rotation and revolution. Just as our moon always shows the same face to Earth, tidally locked planets always show the same face to their stars. The day side bakes under continuous stellar radiation, while the night side never receives a single ray of direct starlight. The climate extremes this creates would challenge even the most robust planetary atmospheres. Proxima b almost certainly exists in this configuration. A planet orbiting just 7.5 million kilometers from its star experiences enormous tidal forces that gradually slow its rotation until one hemisphere permanently faces the stellar surface. The gravitational gradient across the planet's diameter creates differential forces that act as a persistent brake on its rotation. Over millions of years, this braking effect operates inexorably until the planet reaches tidal lock, while the time frame depends on specific planetary properties. For worlds in the habitable zones of red dwarfs, the process completes within hundreds of millions of years at most. Proxima b has orbited its star for billions of years. Therefore, tidal locking is not just a possibility for this world, but a certainty. The planet turned one face permanently toward Proxima Centauri, long before complex chemistry could have organized itself into anything resembling life. While the James Webb Telescope cannot directly image the surface of Proxima b, spectroscopic analysis of how starlight interacts with the planet during its orbit reveals vital information about its temperature. By measuring tiny variations in the combined light of the star and planet, astronomers can tease out planetary signatures from the overwhelming stellar glare. The data confirms extreme temperature differentials consistent with tidal locking. The dayside reaches temperatures where rock would glow red-hot, perhaps 1,300 Kelvin or higher. Meanwhile, the night side drops toward temperatures where even carbon dioxide would freeze solid, approaching 100 Kelvin or lower in the absence of any heat transport mechanism. This difference of over 1,000 degrees is far larger than any temperature differential found on Earth. The traditional habitable zone concept assumes planets can distribute stellar energy across their surfaces through atmospheric circulation. Hot air should rise on the dayside, flow toward the night side, cool and descend, then return to the dayside to repeat the cycle. This circulation is supposed to moderate temperature extremes. With sufficient atmospheric mass, even tidally locked planets might maintain liquid water. However, James Webb's findings suggest Proxima b lacks the atmosphere necessary for this mechanism to operate. No atmospheric signatures mean no atmospheric circulation. Heat cannot be transported through air currents that do not exist. The thermal extremes created by tidal locking generate their own atmospheric destruction mechanisms. Even for planets that initially possess substantial atmospheres, gases migrate from hot regions toward cold regions. On a tidally locked planet without heat distribution, atmospheric gases flow from the hot day side toward the frigid night side. Upon reaching that darkness, these gases cool, condense, and deposit onto the surface as frost or ice. This process, called atmospheric collapse, can strip a planet of its gaseous envelope through purely thermal means. Water vapor condenses into ice. Carbon dioxide freezes into dry ice deposits. Even nitrogen might eventually accumulate in these cold traps. The atmosphere gradually transfers from a gas surrounding the planet to a solid layer on the nightside surface. Atmospheric collapse alone would doom habitability, but Proxima b faces this in combination with relentless stellar radiation. Even if volcanic activity released new gases, they would either be stripped by stellar winds or migrate to the night side and freeze. This creates redundant destruction mechanisms that ensure atmospheric loss cannot be reversed. James Webb also detected the stellar wind emanating from all three stars in the system streams of charged particles, accelerated outward by magnetic forces. These particle flows create invisible rivers of plasma that wash over any planets in their path. Our Sun produces a stellar wind carrying roughly 1 million tons of material into space every second. While that sounds enormous, the density is low by the time it reaches Earth, allowing our magnetic field to deflect it. This deflection creates the magnetosphere, a protective bubble that shields our atmosphere. Without this shield, stellar wind would strip away atmospheric gases through sputtering, where incoming particles knock molecules to escape velocity. Mars serves as a cautionary example. It once possessed a thicker atmosphere and potentially liquid water, but it lacks a global magnetic field to deflect the solar wind. Over billions of years, the solar wind stripped away most of its atmosphere, transforming it into a cold desert. Proxima Centauri produces a stellar wind that makes the solar wind seem like a gentle breeze. James Webb measured particle emission intensities from this red dwarf and found wind densities hundreds of times greater than solar levels. A planet in its habitable zone experiences bombardment that would overwhelm any plausible magnetic field. The enhanced stellar wind results from the same magnetic activity that produces frequent flares. The churning convective interior accelerates particles to high velocities, creating a wind of exceptional density. Even Earth's robust magnetosphere would fail here. Our magnetic field deflects the solar wind at a standoff distance of several Earth radii, but if the wind were hundreds of times more intense, this distance would shrink dramatically. The magnetopause would be pushed so close to the surface, perhaps even below the top of the atmosphere, that molecules would be exposed directly to particle bombardment. The stripping process that transformed Mars would operate with even greater efficiency. The absence of atmospheric signatures from Proxima b is not a mystery. It is the predictable outcome of physical processes operating over billions of years. The planet lost its atmosphere because it lacked the protection necessary for retention under such intense bombardment. The radiation prison has no visible walls, only consequences that accumulate until nothing remains. The radiation prison surrounding the worlds of Alpha Centauri is not merely a physical barrier. It is a chemical executioner that dismantles the very building blocks of life. Even if a planet could somehow cling to a sliver of its atmosphere or maintain a stable temperature, it would still face the relentless assault of extreme ultraviolet radiation. Ultraviolet light carries enough energy to shatter the chemical bonds within atmospheric and organic molecules, a destructive process known as photolysis. This phenomenon is the ultimate architect of sterility. On Earth, we are familiar with ultraviolet radiation as the cause of sunburns, but our planet possesses a sophisticated defense system. High in our stratosphere, a layer of ozone absorbs the most damaging ultraviolet wavelengths before they can reach the lower atmosphere and the surface. This ozone layer is itself a product of life's long history. It was created by the photolysis of oxygen molecules produced by photosynthetic organisms over billions of years. It is a self-maintaining shield that allowed life to finally colonize the land. However, Proxima b and the hypothetical worlds of Alpha Centauri A and B lack this protective pathway. Without a substantial atmosphere to facilitate ozone formation, ultraviolet radiation from the stars reaches the planetary surfaces at full, lethal intensity. Every organic molecule exposed to this light, the amino acids, nucleotides, and proteins necessary for biology, is broken down into simpler, inert compounds within hours. Laboratory experiments have demonstrated that these biological precursors decompose rapidly under ultraviolet intensities far lower than what Proxima b experiences every single day. During stellar flares, this sterilization is accelerated, creating periodic events that would eliminate any surface life that somehow managed to survive the baseline radiation. Some researchers have clung to the hope that subsurface environments could provide a refuge, much like the deep oceans sheltered early life on Earth. This hope, too, has been undermined by the precise measurements of the James Webb Telescope. The high-energy particles unleashed by stellar flares possess such incredible velocity that they can penetrate meters of solid rock before their energy is fully absorbed. To be truly safe, an organism would need to be buried under tens of meters of stone. But such deep, isolated environments are disconnected from the energy sources and chemical flows necessary to sustain biological processes. You would not be living in a sanctuary, you would be living in a tomb. The timeline of this destruction is perhaps the most devastating realization. Life on Earth required approximately 500 million years to emerge from prebiotic chemistry. This process required stable conditions for complex molecules to accumulate and interact over geological timescales. But the atmospheric stripping and chemical destruction observed in the Alpha Centauri system operate on timescales of only tens of millions of years. The chemical foundations of life are erased faster than biology can bootstrap itself into existence. This leads us to the problem of water, the universal solvent of life. Even if a planet in this system formed with abundant water, the radiation environment ensures its permanent loss through a process called desiccation. Ultraviolet photons dissociate water molecules into their hydrogen and oxygen components. On an airless or thin atmosphered world, the lightweight hydrogen atoms escape into space permanently over billions of years. Even a massive ocean would be transformed into escaping gas and surface oxygen that binds to rocks. James Webb's data suggests that Proxima b has been completely desiccated, its water long gone, leaving behind only a parched and barren landscape. The very mineralogy of these worlds bears the chemical scars of this bombardment. High-energy particles and ultraviolet photons alter the chemical state of surface materials through radiolysis and photolysis. Minerals containing water or hydroxyl groups lose these components, while organic compounds delivered by asteroids are broken down almost instantly. Every exposed surface in the Alpha Centauri system has been space-weathered into a state of chemical simplicity. The crystalline structures of minerals are displaced and damaged, eventually becoming amorphous and losing the ordered structure that characterizes the geology of a habitable world. The comprehensive picture painted by these findings is one of absolute sterility. Every mechanism that might protect habitability atmospheres, magnetic fields, oceans, or subsurface refuges fails under the conditions measured by the James Webb Telescope. The radiation prison has no exits because the bars are made of fundamental physics. The nearest stars shine not on homes for life, but on rocks, scoured clean of any possibility for biological complexity. We are forced to confront the fact that the cosmic house next door is not merely empty, it is uninhabitable. The findings delivered by the James Webb Space Telescope regarding Alpha Centauri represent more than just a collection of disappointing data points. They represent a fundamental shift in our place within the universe. For decades, the search for extraterrestrial life was fueled by a manageable, almost comforting assumption. We believed that if planets were common and habitable zones were abundant, then the galaxy must be teeming with life. Alpha Centauri was the ultimate litmus test for this optimism, the closest and most accessible laboratory to prove that we were part of a crowded cosmic community. That test has failed comprehensively. The silence echoing from our nearest neighbors is not a result of technological failure or inadequate search strategies. It is the silence of a genuine, profound loneliness. James Webb has shown us that the cosmic house next door is not just quiet, it is dead. The Great Revision. The implications of this sterility ripple outward, forcing a radical revision of the Drake equation, the mathematical framework we use to estimate the number of active, communicative civilizations in the Milky Way. For years, we plugged in optimistic numbers, imagining billions of Earth-like worlds. But the Alpha Centauri findings suggest we must apply a series of brutal filters. The red dwarf filter, roughly 70% of all stars are red dwarfs like Proxima Centauri. If Proxima is typical, and James Webb's survey of dozens of other red dwarfs suggests it is, then 70% of the galaxy's stars are hostile to life due to violent flares and atmospheric stripping. The binary filter, about half of all sun-like stars, exist in binary or multiple systems. The Alpha Centauri result demonstrates that binary separations in the range of 10 to 50 astronomical units can catastrophically disrupt planet formation in the habitable zone, the stability filter. Even in the rare cases where a planet forms, it must maintain geological and orbital stability for billions of years to allow for the slow crawl of biological evolution. When we account for these filters, the estimated population of habitable worlds shrinks from billions to perhaps mere thousands or millions scattered across a galaxy of 400 billion stars. The distance between these rare oases might not be 4 light-years, but tens of thousands of light-years, a universe of isolated islands. This distance is a barrier that no known physics can overcome. Even at the speed of light, communication would take tens of thousands of years for a single round-trip exchange. A message sent today would receive a response only after the civilization that sent it had evolved beyond recognition or vanished entirely. Physical travel is even more daunting. A probe traveling at 1% the speed of light would require 100,000 years just to cross 10,000 light-years. The reality James Webb has uncovered is that we may share the cosmos with other conscious beings while remaining effectively alone. We are isolated islands of awareness in an immense, indifferent ocean of stellar fires. This is perhaps the simplest and most disturbing resolution to the Fermi paradox we haven't heard from anyone, because habitable worlds are far rarer than we dared to imagine, and the few that exist are separated by the insurmountable geography of space-time. The preciousness of the pale blue dot, however, this restriction of possibilities should not inspire despair. Instead, it should transform our understanding of our own planet. If the conditions for life are as rare as James Webb suggests, then Earth is not just one of many. It is a miracle of staggering proportions. Our planet formed around a stable, solitary star with gentle radiation. We possess a robust magnetic field that deflects the solar wind, and an atmosphere that filters lethal ultraviolet rays while allowing the light for photosynthesis to pass through. Our geological activity recycles nutrients and maintains our climate over billions of years. Every single one of these circumstances could have been otherwise. The Alpha Centauri observations remind us that there is no planet B waiting for us, just around the corner. There is no backup sanctuary if we fail to sustain the conditions that make our world habitable. This perspective transforms environmental ethics from a local political concern into a cosmic imperative. We are the temporary observers of eternal processes, the brief sparks of consciousness in an overwhelmingly unconscious cosmos. The final truth, humanity's first steps beyond our solar system, will not begin at Alpha Centauri. Any future we build among the stars must aim at destinations far more distant, requiring technologies and timescales far beyond our current reach. The cosmic neighborhood is not what we hoped for, but the truth, however harsh, is more valuable than a comfortable illusion. As the golden mirrors of the James Webb Space Telescope continue to collect ancient photons, we will continue to listen and wonder. We may eventually find that we are not alone, but we must accept that for now, and perhaps forever, we exist in cosmic isolation. Our nearest stellar neighbors offer only the profound silence of worlds that never were and never will be homes for life. we are left with the cold, clear truth of our own uniqueness and the absolute necessity of protecting the only world we have ever known.